In the third part of our SUVAT equation derivations, we're going to consider the case with acceleration and initial velocity. We began by considering the case of constant velocity, then zero velocity with constant acceleration. Now we're going to combine the two, have initial velocity and have acceleration occur. This word problem summarizes the typical types of things that you might see in this kind of situation. So we have a car rolling into the Easy Paths booth and is 3 meters west of the Easy Paths booth. So here's our reference point of 0, and this is our Easy Pass right there. We have an east-west situation again, so we have east positive and west negative. We're told that at the outset it's 3 meters west, so we have an XO of -3, but it is already moving, has an initial velocity, V0, of 4 meters per second east, and then it accelerates. In each interval of time, it will travel faster and faster as it gets faster in the easterly direction, increasing its speed by 2 meters per second every second. So that's our situation. So we can see that after a period of 5 seconds, it is going to be somewhere here east, certainly more easterly than where it started, and perhaps even off this number line. And we will determine that. Now, before we start our graph, we always want to analyze the bits of information we can glean from the graph. We can always read the axes, which is velocity and time. We can determine the gradient, and the gradient in this case is delta V over delta T, which is the acceleration. And the area, we know, is the displacement, or delta X. We've also, in the past, discussed that we should examine our velocity formulas and our acceleration formulas. So let's first start with our velocity formulas. Well, to get a handle of this, the velocity formulas, we need to plot the points on the graph. So we know that in terms of velocity, we have an initial velocity of 4 meters per second. So that means at time 0, the initial velocity is 4. And that velocity is going to increase by 2 meters per second every second. Now we can see here the dark lines are increments of 4, so halfway is 2. So after 1 second, it will increase to 2. Increase 2 to 6. And after another second, it will increase 2 more to 8 meters per second. And after another second, it will increase to 10. And after another second, it will increase to 12. And after the 5th second, it will increase to 14 meters per second. So we can see, as we saw in the last example, with uniform acceleration, constant acceleration, we will get a straight line on a velocity time graph. So we now know that the function we're dealing with is a straight line, the function of the velocity. Well, the generic equation of a line is y equals ax plus b. The y-axis on this graph is velocity. The gradient of the graph is acceleration, coincidentally the same letter. The x-axis is time. And the y-intercept in this case is the initial velocity, which is u in the SUVAT equations. In the more advanced equations, it's at plus v0. So what we see here are 2 new equations or expressions for the velocity. Now, what we're looking for is ultimately the position of this car after a period of time, and to get to the position, we need the displacement. The displacement is the area. So the area the first 5 seconds is this peculiar shape, which at first I will draw your attention to the fact that it is a non-standard trapezoid. You recognize that this side and this side are parallel, and it has 4 sides. But it also is built up off a rectangle and a triangle. We are first going to examine it as the trapezoid. Now we examine this as a trapezoid using SUVAT. We have the area of a trapezoid, which is 1/2 base 1 plus base 2 times the height. So in this case, we have a base and we have a base. So we have 1/2 base 1. I will call base 1 this value here, which is V. But you can see that that value changes. Well, the V is AT plus U. So this B1 is AT plus U. Base 2 is this side over here. In fact, I'll label it B1, B2. And base 2, in this case, is this value, the initial velocity, plus U, times the height. Now the height in this case is this side here, which is t, the time. So now in terms of this expression here, there are 2 things I can do. First is I can combine like terms with the u's, and I can distribute the t. I'm going to do both in one step. Is 1/2 distributing the t, at squared, and this becomes 2u, and distributing the t becomes 2ut. Going further, in distributing the 1/2, we get 1/2 at squared plus ut. And that gives us the displacement, s, in the SUVAT equations. Now, in our advanced formula, we know that the only thing that's different is the variables themselves. So with our advanced, we'll start out with s equals 1/2 at squared plus ut. Now in the advanced formulas, displacement isn't s, it's delta x. And we have 1/2 the acceleration times the time squared used in both systems. And the initial velocity is v0. So those are our 2 equations for the displacement when we have an initial velocity. So what is this? Let's evaluate this at 5 seconds. What is the displacement? Well, delta x is 1/2 the acceleration, which is 2, 5 seconds, initial velocity of 4, and the time of 5 seconds. So we end up with a displacement of 25 plus 20, or 45 meters. In other words, the car will be 45 meters eastward from where it was at the outset. It'll be displaced positively 45 meters. Remember, the sign of the 45 is positive, so the displacement is positive 45. At the outset, I mentioned that we could obtain the area through a trapezoid, or we could view the area as this triangle and this rectangle. If you remember from the previous screencast on acceleration from rest, we had a curve like this, straight line, but it came out of the origin. And the result of that was this 1/2 AT squared. So there's some of this displacement that's due to this 1/2 AT squared term, and there is some of the displacement that's due to the initial velocity. If we look at this term here, V0t, V0t is really this side times this side. So this term is the area of the rectangle, and this term is the area of the triangle. The next thing for us to consider with this example is the position. Now, in the last examination, we knew that delta x is 1/2 AT squared plus V0t. But by definition, the change in position, the displacement, is x minus xo. So substituting in, we get x minus xo equals 1/2 AT squared plus V0t. So what is the position x? If we add x0 to both sides, we get x equals 1/2 AT squared plus V0t plus xo. So this is now the equation for the position. Well, let's evaluate it. Our acceleration was 2, time was 5, our initial velocity was 4, time was 5, and our initial position was -3. 25 plus 20 minus 3 gives a position of 42 meters. Well, let's see if this makes sense. We have a position of 42 meters. We computed a displacement of 45 meters. They disagree with each other by 3 meters. Let's see if we can figure out why. The displacement is 45 meters in this direction. But this position is 3 to the left. So if you take off 3 out of that 45, that leaves 42. So it'll be positive 42. So that answer does indeed make sense, 42 meters as the position. So now let's quickly examine the summary of the formulas we've looked at in this screencast. Now these formulas should be looking very familiar to you. We have S equals 1/2 AT squared plus UT. This will give us the displacement. This one will give us the displacement. And as I just pointed out, delta x is x minus x0. So if we substitute x minus x0, we end up, and we add x0 to both sides, we end up with this equation for position, something we can't get with the SUVAT equation. The two formulas for velocity now take into account the initial velocity, being u in SUVAT and xo, and our acceleration equations remain the same.